We continue our discussion on differential geometry based analysis of local surface geometry. And in the last lectures, we discussed that how normal at a surface point could be computed, and we have defined two particular entities describing the local surface characteristics. One is first fundamental form, the other one is second fundamental form. In the first fundamental form, essentially we are computing the magnitude of the change of the gradient at that point, or magnitude along the tangent vector, and in the second fundamental form it is related with the computation of curvature, and we will continue our discussion on this particular aspect. So, we are using the parametric description of a surface point, say u and v are the parameters, and normal at tangent at a surface point can be computed in this form, where u and v both again can be expressed in terms of a parametric curve descriptions. And then if I induce a curve on the surface, we have used this parametric representation, say beta t, which is once again defining the surface point u t b t for t within certain range. It could be 0 to 1, it could be any other values of the real interval. So, with this description, we at a particular value of t, we can compute the normal, we can compute the tangent of that curve by taking the derivatives along t. So, this is how the derivatives could be computed for the functions, as we have seen that the x can be derived with respect to u and then u with respect to t. So, the chain rule is applied here. So, this is how the tangent vector is computed at the point. We have already discussed this also earlier. And then the second fundamental form is defined in this fashion, which is the t dot differential of n t. That means, as you move across the along the tangent, how the normal is changing its direction. So, that is the vector, that changing vector, that vector representing that change of normal. So, you are taking the dot product of these two, and then you will be getting the second fundamental form, which actually measures the local curvatures, which represent the which is a measure of local curvatures, and which is defined from the functional point of view in this fashion. So, with the same descriptions, here you can see E, F, G, they are again three entities, three parameters which are related to these functions, and this is the definition of small e, f, g, which are all related to the second fundamental form, those parameters. So, they are the dot product of the normal at that surface point, and also the second derivative vector of the variations along constant v curve. This is second derivative vector variations along both u and v directions, and this is first derivative with respect to u, then second derivative with respect to v. So, we understand this kind of interpretations of differential calculus or differential, that is the definition. And so, normal curvature is actually has to be normalized with respect to the magnitude of the tangent. So, it is the second fundamental form that should be normalized, and these are the expressions. So, this is what is normal curvature, which is second fundamental form to be normalized, and as you can see, this is the expression for normal curvature at surface point for the curve described for any particular curve described by this parameter t, and and also the corresponding in the tangent directions along that curve. So, for any tangent direction, this is the definition, and these are the quantities which are defined earlier, that E, F and G, these are already defined here, and capital E, capital F, capital G, they are related to the first fundamental form. And what if we can remember that E should be x u dot x u, then F is x u dot x v. So, these are all capital X, that is a surface point, and G is x v dot x v. So, they are the magnitude of the tangents along the constant u, constant v, and the other is basically the dot product of two tangents along constant u and constant v curves in this description. So, these are the interpretations from the functional point of view. So, let us continue that how this could be further used for computing curvatures locally. So, there is a concept called linear map using these parameters, and this linear map, it contains all the necessary informations for computation of curvature. So, this linear map is defined in this way. You can note that the inverse of the parameters of first fundamental form is shown by this matrix capital E, capital F, capital G. These are the elements, those inverses are shown. So, this is related to first fundamental form parameters, and these are related to second fundamental form, and those definitions can be seen here, how we have defined earlier also in this case. So, how linear map is characterizing, let us see. So, in the linear map, the eigenvalues and eigenvectors, they provide the principal curvatures and also the principal directions corresponding to those principal curvatures. So, these are interesting, and we can say that it is basically one of them would be dominant curvature whose value is greater, but note that there is sign involved. So, in the case of computation, we may we call them two principal curvatures, but since there is sign involved, actually when we are considering with respect to their relative strength, then the magnitudes should be considered. Earlier we have seen this particular feature when we have detected the Harris corner, and we have considered the magnitudes of curvatures there. For a two-dimensional function, of course, in that case, which is equivalent to a function in the surface also is a two-dimensional function. So, these analyses are can be quite extended in that scenario also, except that is not a surface, that is a brightness distribution or any other functional distribution. So, anyway, coming back to this particular topic of surface geometry. So, curvature is a very critical information to understand the local surface topology or geometry. And so, there are two entities which are very intrinsic, one entity particularly Gaussian curvature, which is very intrinsic property of the surface geometry, and that could be computed as the determinant of linear map, which is actually product of these two principal curvatures. And mean curvature, it is basically half of the trace of linear map, or which is the mean of the two principal curvatures. So, these two also can be an alternative descriptions of local curvatures other than the principal curvatures. So, the expression for mean curvature can be obtained using the parameters of first fundamental form and second fundamental form that is given here, and also the expression for Gaussian curvature is also given here. You note that since this is a very familiar expression which can be related to the theory of quadratic equation. So, we can define a quadratic equation. This is equation and its solution is also shown here. So, you can also get principal curvatures given mean curvature and Gaussian curvature. So, the usefulness of this analysis can be understood through this by this particular technique, which has found the topology of the local surface curvature. You can see various kinds of local shape that could be attributed by the signs of, in this case this is shown with respect to Gaussian curvature and mean curvature. So, if the mean curvature is negative, so if it is negative and if the Gaussian curvature is positive, then it is like a surface, like a peak surface. Just to draw your attention to the fact, in our school geometry also we know that when you have a function as a variable of x and if we get a peak here. So, at this point the peak maximum could be characterized when we find its double derivatives. That means, if I take the f double dash x, double derivative of x, that is less than 0. Whereas, if it is a minimum, then f double dash x is greater than 0. We have already know this particular feature and it can be explained from differential calculus. From there we can explain why the signs should be here negative and positive respectively. And we also know that this maximum and minimum, they are characterized by the gradient value that should be equal to 0. However, the fact is that, see, this curvature, it is related, it is proportional, almost proportional to this differential double derivative of the functional value. So, in a surface again we can consider any particular curve and which has this kind of shape. So, we expect the curvatures values, so principal curvatures should be negative here and all the principal curvatures. So, there are two directions. So, if I consider these are the two principal directions for principal curvatures. So, both should be negative, then you can get this kind of peak shape. That is what is expected here, and you know that the mean curvature, it's defined as the mean of these two value. So, since they are negative, so mean also has to be negative, and the Gaussian curvature, which is given by capital K, it is defined as product of these two values, and since once again they are negative, the product has to be positive. So, that is how this characterization of if the mean curvature is less than 0 and Gaussian curvature is greater than 0, then you can characterize it as a peak surface. Similarly, for the pit surface, which is like the minimum of a one dimensional function. So, this is a scenario, this is a pit surface. Here we expect both of them should be positive, both curvature should be positive. So, the mean curvature should be positive as well as the Gaussian curvature should be positive. That is what is shown here. So, you can extend this analysis. For a flat surface, these curvatures are going to be 0. We know that radius of curvature is infinite for a flat surface. So, the value of curvature is 0. So, since for a flat surface value of curvature is 0 at any directions, so you get both of them 0, Gaussian and mean should be 0. So, you extend this kind of observation to various other shapes in a 3-dimensional surface, and you can explain the kind of features or observations, those are provided in this particular slide. and in fact, this is the paper which discusses these particular properties. This is a paper by Paul J. Bessel and Ramesh Chandra Jain. In 1986, it was published, and it is a very pioneering paper in characterizing the or in finding out the local topology of range images from the range image, from the range data. So, this shows how we can compute these particular characteristics, local properties, and this feature again you can use for your purposes later on, for example, segmenting surfaces, etc. So, just to summarize, we can characterize this local topology by the signs of curvatures. It could be signs of principal curvatures, or it could be signs of Gaussian and mean curvatures. So, you can see that for the principal curvatures, as I mentioned, we have, when both are negative, we have peak, when both are positive, we have pit, and then there are combinations of negative positive, positive negative. So, they have a almost like a symmetric relationships you can find out in this case. You have say ridge, ridge, saddle, saddle. Because of this, see it is it does not matter in which direction it is negative or positive, but the local surfaces, they will have symmetric. This property can be described in the form of a symmetric matrix form. You can say it has certain symmetry with respect to this. Whereas for Gaussian and mean curvatures, the characterization is a bit more elaborate that you can see here, and that is the reason why in the previous work of Bessel and Jain, they have used Gaussian and mean curvatures. It is interesting, they have identified these characteristics. So, there are regions like saddle ridge, which was earlier could not be characterized, or saddle valley, minimal surface. So, these are few other kind of characterizations, other kind of topologies also they have considered in their analysis. So, we will be considering a special kind of surface description, and which is akin to our range data. And in fact, there is a term of this kind of surfaces, surface patches, when you consider the parameters u and v, they itself describes the x coordinate and y coordinate, and the z coordinate is a function of those two parameters, like h u v has been shown. So, this is a familiar range data representations what we have discussed in our previous lectures, and one example is shown here in the as a figuratively. So, this is a surface patch, and this is u and v, like it is equivalent to x and y axis, and you get the corresponding height of the surface point from that plane, which is the z directions. So, this is how this is described, and from this already we know in general, for any description of parametric surface, we can compute the surface normal and then all the elements of first fundamental form and second fundamental form matrices in this form. So, this is, note that this is second fundamental form matrices. So, these are all double derivatives, they are related to curvatures. So, this is the second fundamental form matrices, and this is the first fundamental form matrices. These are all derivatives, and they are related to the magnitude of the tangents, or actually this is a dot product of tangents along two directions, two different directions for f, otherwise they are also of the same directions. So, these quantities can be computed now easily. I mean, they have a special form in this particular aspect, because if I compute x u, then if I take the gradient and let me represent them in the form of a column vector. So, you get 1 0, and let me write it as h u in short. That means, it is the derivative h u is a partial derivative of function h u v with respect to u. Similarly, we can compute x v as 0 1 h v. So, from these two vector we can compute E. So, what should be E? E is x u dot x u, which will give you 1 plus h u square. Then F is x u dot x v, which will give me h u dot h v, and G is x v dot x v, that magnitude itself, it is 1 plus h v square. So, this is about the elements of the first fundamental form. What about the elements of second fundamental form? Again from this description. So, let me first compute the normal vector, because it requires to computation of normal, and for that I need to take the first cross product of x u and x v. So, I will use that familiar cross product computation. So, this is, I will expand this determinant, and this could be written as, so this is minus h u I plus this is minus, this should be v, this is v, minus h v this is minus h v j, and k is 1. So, this vector n can be considered as, this vector is minus h u minus h v 1, and if I have to normalize it. So, n is given as minus h u minus h v 1 divided by root over 1 plus h u square plus h v square. And from there you can compute now the other thing. So, if I consider x u u, which means I have to once again take the derivative with respect to this, and we will get 0 0 h u u, and x u v is 0 0 h u v, and x v v is 0 0 h v v. So, your value of E should be dot product of n and x u u, and only the z component. So, you have h u u by root over of 1 plus h u square plus h p square. And similarly, I mean for f it is minus h u v by this magnitude, and for g it is a minus, no, all are minus, minus is there. So, this should be minus. So, so that should be again minus h v v of this. So, this is how these elements are computed, just I have described, and let us see the result, how we can get it. So, you see that what I have described, those are the things mentioned here, and once you have computed this, then you can compute the Gaussian curvature and mean curvature using this particular using this element. So, linear map, you know, linear map is given by E f f g, and this is the inverse of the first fundamental form matrix. So, you can compute those quantities and then take the trace of the matrix, half of the trace, and determinant of the matrix, then you can get the Gaussian curvature and mean curvature. And from there also you can get also principal curvature. So, I will show you the expressions of Gaussian curvature and mean curvature as a result of this operation. So, this is how you will get mean curvature, this is the expression, and also the Gaussian curvature, this is the expression. So, when you have a range data, then you can compute these curvatures by using this particular these expressions, because range data, as I told, that is a simplified form of surface description, where the parameters are described itself by the x and y coordinates in those directions, and the depth value is a function of x and y coordinate, which is a z coordinate. And by computing them, you can compute the derivatives using the masks, as we have discussed earlier in our lectures. In the very first lecture, we discussed how derivatives could be computed, even the double derivatives, other gradients could be computed of a function, of a two-dimensional function that we have discussed. So, use those masks to compute these derivatives, partial derivatives and also double derivatives, and then from there you can compute the mean curvature and Gaussian curvature. Then look at the signs of those curvatures, and that would give you the topology of the local surface. So, with this, let me stop here. We will continue this discussion of surface geometry, local surface geometry in the next lecture. Thank you very much for your attention.